Hello, chemistry students. We're here to do lesson 5.2, which is the introduction to ions.
And our first objective is to learn the properties of ionic compounds.
And then we're going to show you how to determine the charge on some of the ions using only your periodic table. And we'll also, along the way, explain what we mean by an ion and what some of the different kinds of ions are.
Alrighty,
Let's get started.
Alright, so the first definition for this chapter is an ion. An ion is an atom or a molecule with a non-zero charge created by gaining or losing one or more electrons.
So we kind of have taught you that atoms are neutral. They have just as many electrons as they have protons. And although they might start out that way, they don't stay that way. For reasons that we're going to discuss, they may pick up an extra electron or more than one extra electron, or they might lose them, and then their charge is no longer neutral, no longer zero. It's either going to be positive or negative, which leads us to the two main kinds of ions.
So the first type is the anion. This one is gain one or more extra electrons to become negatively charged.
Okay, so the way that you remember it is a negative ion. Anion just means negative. They have extra electrons above and beyond their number of protons.
All right, and the second type is a cation. That's where you lose one or more electrons to become positively charged.
So again, if you write the word cation and you change the T to a plus sign,
okay,
you're going to remember that cations are positive.
Or cats are just always in a good mood. I don't know. All right, let's go on to the next thing. All right, with the introduction of ions, we can now combine ions with the electron configurations that we did from last chapter. And as you see, we have potassium's longhand written out. We did that on purpose. You can read it as it is: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 is the ground state electron configuration for elemental potassium. Now, as we said, ions, they have to gain or lose electrons.
And potassium's a loser, isn't it?
Yeah, because it's a metal. Metals like to lose their electrons and go to the next noble gas configuration. So to get to that noble gas configuration, they're going back to argon, which means they lose that 4s1. So it becomes a 1s2, 2s2, 2p6, 3s2, 3p6. And that, if you were to write it out for what it looks like as an elemental symbol, the ion symbol is just a capital K, but then you put a plus or a plus 1, depending on what you would like to see. Now, the same goes for oxygen. It has a 1s2, 2s2, 2p4, but since it is a non-metal, it's to the right of the stair-step line, they gain electrons. And
it's a lot closer for oxygen to get to a noble gas by gaining electrons.
Yep. So oxygen is 2 away from neon, so oxygen is going to gain 2 more electrons. So it becomes 1s2, 2s2, 2p6, and that's the difference. And its ion symbol is O2 minus.
Or you can write it O minus 2.
Yeah.
It makes no difference.
You'll see it usually, I think, 2 minus in books, but it's... Anyway, a big point to point out here is at the bottom. It says ions form the way they do because they want to get to their more stable noble gas electron-like configuration.
And that's kind of the theme throughout. Basically, that's the noble gases have the most stable of all electron configurations. So any kind of chemical bonding action and reactions that happen are going to
go to a more...
the electrons being in a lower, more stable, lower energy state.
That's correct.
Like that noble gas. So we'll expand on that more later. But for now, we just want you to be able to recognize when this is how you're going to write an ionic symbol. We generally don't show the entire electron configuration. We just show the element symbol and what its overall charge is.
All right, let's go on to the next thing. All right, so there are general properties that ionic compounds, which are compounds formed from cations and anions, all contain, or contain most of these properties. So a general property of most ionic substances is, first of all, they are brittle, meaning easily broken up.
Okay, they're also going to tend to be very hard, so they're going to be difficult to crush. But if you do succeed in crushing one, like Mr. Hunter just said, they're brittle, they're going to just break up into little pieces. They don't dent or deform in any way.
All right, the next is they have high melting points. It's very difficult to melt pure salt, which is an ionic compound. They have very high melting points.
Okay, they will, at least most of them, when they're dissolved in water, and most of them like to dissolve in water, they will separate into their ions. So instead of being a compound now, they're going to be kind of free-floating mixture of cations and anions.
The word for that's dissociate or dissolve. The next one is many are soluble in water. They will dissolve in water and be a homogeneous solution.
Okay, because when they dissolve, those ions separate. Now you've got mobile charges in there, and so they're really good conductors of electricity when you dissolve them, or because for the same reason, when you melt them, if you do get them hot enough to melt them, those ions are separate from one another, so they can carry charge around.
There's some very interesting chemistry dealing with molten state ionic compounds. Anyway, they do not conduct when they are solid. If I were to put an electrical current in solid salt, nothing would happen.
Because the ions are not mobile now.
Yep.
They're locked in their position. So which brings us to, they exist in their solid state as a crystalline solid. They're going to always be composed of crystals, sometimes smaller, sometimes larger. And those crystals have what we describe as a lattice structure. There's a very organized arrangement, a pattern to how the ions are packed together.
All right. And then lastly, the compounds are held together in a lattice by electrostatic attraction.
Which just means that positives
Attract negatives.
So those are, we have some labs that we're going to have you do where we explore differences between compounds that are held together by ionic bonds and covalent bonds. And you get to see this firsthand. All right, let's go on.
All right, pictured here is an example of a lattice structure. You can see that these things are drawn together in kind of a square, and that they alternate in their location, and it's uniform throughout the entire thing. And this is known as a formula unit of the lattice structure, and you can just see how it alternates.
It doesn't really say on here which ions these are, but I'm guessing, if the green ones are negative, the blue ones are probably a positive ion.
Yep.
Not sure what the red one is in the middle, but all of the different ionic substances are going to have some sort of a regular repeating arrangement of their ions, similar to this. And the gray things would represent those electrostatic attractions that are holding them together.
Okay. All right, so once again, the periodic table becomes a huge help in figuring things out in this class. We have different groups listed below, 1, 2, transition metals, 18, 17, 16, 15, and 14. These are the main ions that we're going to be looking at.
These are ones that you can always know their charge just by looking at where they are on the periodic table.
That's correct, yeah.
But the transition metals is a little foggy, but we'll address that.
All right, so the first one we're looking at is the first column of the periodic table, known as the alkali metals. They have a ground state electron configuration that ends in S1. So they want to get to their closest noble gas. So instead of gaining 7 electrons, once again, metals like to lose electrons. So it's going to lose that electron to gain a positive 1 charge and go back to the noble gas configuration that would be something P6. So either take 2p6, 3p6, or something like that. So the group 1 has a charge of positive 1.
So they're always, you don't even really have to ever question if it's a group 1, it's going to make a +1 ion.
The same logic can be applied to group 2. They have an ending of S2. So again, it's easier to lose 2 electrons than it is to gain 6. So their charge is positive 2.
Again, always, without exception.
We're going to go to the transition metals next, which are the ones in the center. These are a special group that use something called Roman numerals to describe their charge. And they can do this because they have a varying amount of electrons, which can be removed in various amounts of ways. So we're just going to kind of gloss over them for now, but the transition metals are various charges. Anywhere from positive 1 all the way up to positive, I think 6 is the largest one. All right, the next one we're going to talk about, we're going to...
So just to, we'll cover some of the cases in the transition metals later, and there are some, charges that you can know, but they're kind of, like Mr. Hunter said, all over the place. There's no, there's a pattern there, but it's a little more intricate and obscure than the ones. It doesn't go by just straight up which row they're in or which column. So enough said on that.
All right, the next one we're going to go back. We're going to go all to the right side of the periodic table to the noble gases. They are special because the word noble refers to the fact that they do not react easily, so they do not form charged species. They have the P6 ending. They don't want to gain or lose electrons, so they are happy. They form a charge of nothing, so they form 0.
So they're basically not going to make ions.
The second row that we're going to look at now, or the next row is 17, the halogens right next to them. They are at the P5 at the end of their configurations, P5. So again, for them, it's easier for them to gain 1 electron.
Yeah, they're just one away from being a noble gas.
So they're just going to pick up another electron, so they have a charge of -1. Same logic for the next column, column 16.
So my columns are a little, that's -1 goes there.
So for the chalcogens, which is the term for this column, they have a charge of -2 because they have a P.
They're all going to end in P4.
4. Yes.
Which means they need to get
Two
just 2
electrons.
more to be to that noble gas configuration, and that's what they like to do. So we said that's what, -2?
Mm-hmm. And then 15 has a P3, and they have a -3 charge, and then 14, of course, follows the same trend. It's a P2, and they have a -4 charge. So these are things you just have to know.
So it's just, it's actually fairly straightforward. These two groups of metals are always going to be your +1, +2. And then working backwards from here, don't form ions, -1, -2, -3. Now, there's always exceptions. Notice that, remember our line dividing metals from non-metals, that's separated. So we've got some metals at the bottom of some of these groups. They actually tend to form positive ions, so we'll address that as we go. But the non-metals up here are going to follow these patterns that we wrote right here.
Alrighty, let's go on to the last slide. Okay, here are your PVQs. The first question is, what makes an ion different from atoms?
Okay, and then the second one, we want you to write out the electron configuration for a calcium ion. So you might want to start with a calcium atom, and then look at what group calcium is in. It's in group 2.
And what charge they should form.
And what charge and how are they going to gain electrons? Are they going to lose electrons? How many are they going to gain or lose? And then figure it out from there.
Alrighty.
Good luck. Talk to you tomorrow.